Welcome, everyone. I'm excited to kick off this session on Android interview prep, key concepts. Today, we'll explore the essential topics you need to master for successful Android development interviews. We'll cover core ideas, important skills, and tips to help you prepare confidently. So let's get started and dive into what makes a strong Android candidate. Let's take a closer look at coroutine scopes. First up is global scope, which operates at the application level. While it's available for use, it's generally discouraged in production apps because it can lead to memory leaks and lacks structured concurrency. Next, we have ViewModel scope. This scope is tied directly to a ViewModel's lifecycle. That means it automatically gets canceled when the ViewModel is cleared, helping us avoid resource leaks and managing coroutines more safely. Then there's lifecycle scope, which is bound to a lifecycle owner, such as an activity or fragment. It automatically cancels its coroutines when the lifecycle owner is destroyed. These predefined scopes are really useful because they help us manage coroutines in a lifecycle-aware way, ensuring our app runs efficiently and safely as components are created and destroyed. This ties into our overall theme of writing robust, lifecycle-conscious asynchronous code. Let's take a closer look at Flow versus LiveData. First, with LiveData, one of its main strengths is that it's lifecycle aware, meaning it observes data changes only when the UI component is active, helping us avoid memory leaks. It also delivers updates on the main thread by default, which simplifies UI updates. Since it's part of Android Jetpack, it integrates smoothly with the rest of the Android architecture components. Now, moving to Flow, this is a more general-purpose data stream. Unlike LiveData, it can run on any thread, giving us more flexibility. It offers a rich set of operators that let us transform data streams easily, making it powerful for more complex scenarios. Flow is a cold stream, which means emissions only start when we actually start collecting the data. This makes it efficient. Plus, it leverages Kotlin coroutines, so it's great for handling asynchronous operations seamlessly. Both LiveData and Flow are solutions for data streaming, but Flow really shines when we need enhanced flexibility and power for more sophisticated, asynchronous tasks. Essentially, choosing between them depends on our specific needs, whether we prioritize lifecycle awareness or advanced asynchronous capabilities. All right, let's talk about how we can expose data from our ViewModel using LiveData or StateFlow. The key idea here is to provide immutable streams of data that our UI can observe or collect. This approach helps keep our data flow predictable and easier to manage. For example, with LiveData, we typically use mutable LiveData internally and expose it as an immutable LiveData to the UI. So you might have something like val_name equals mutable LiveData, and then a function load_name that sets the value to John. This way, the UI can observe name for changes, but it can't modify it directly. Similarly, with StateFlow, we use a private mutable StateFlow internally, like count, and expose it as a public StateFlow. We can then have a function increment that updates the count. This pattern ensures that only the ViewModel can change the data, while the UI observes or collects the stream. The UI, whether it's a fragment or activity, then observes the LiveData or collects the StateFlow. This setup keeps our UI reactive and in sync with the data, which is a core part of modern Android app architecture. It all ties back to our overarching goal of creating a clean, unidirectional data flow that's easy to maintain and test. All right, let's talk about view binding versus fine view bind. When I use view binding, one of the biggest advantages is its null safety, which is checked at compile time. This means I won't accidentally get null pointer exceptions because the compiler helps catch those issues early. It also provides type safety, so I don't need to cast views manually, reducing the risk of runtime errors and making my code cleaner and more reliable. Essentially, view binding directly replaces fine view bind, simplifying the process of interacting with views. On the other hand, fine view bind can return null if the view isn't found, which means I have to be very careful and perform manual casting. If I forget, or if the cast is incorrect, it can lead to runtime exceptions that are harder to debug. Overall, view binding offers a safer and more efficient way to work with views, aligning perfectly with the overall goal of making my code more robust and less error-prone. So, what is Hilt? Well, Hilt is a dependency injection library specifically designed for Android. Its main goal is to reduce the amount of boilerplate code we usually have to write when setting up dependency injection manually. As Google describes it, Hilt simplifies this process significantly, making our lives easier. Hilt is actually Google's official dependency injection library, and it's built on top of Dagger, which many of you might already be familiar with. The beauty of Hilt is that it streamlines the setup process in Android applications, so we can focus more on building features rather than managing dependencies. Another key point is that Hilt provides ready-to-use components for common Android classes like activities, fragments, and services. This means we don't have to create these components from scratch. Hilt handles that for us. It also takes care of managing the lifecycle of these components, which helps prevent memory leaks and other lifecycle-related issues. This automatic management ensures our apps are more robust and reliable. And finally, Hilt offers compile-time validation, which means it checks dependencies during compilation. This makes our dependency injection more robust and efficient because errors are caught early, before the app even runs. Overall, Hilt helps us write cleaner, safer code, and aligns perfectly with our goal of building scalable, maintainable Android apps. All right, let's talk about the @Hilt Android app annotation. When you annotate your application class with @Hilt Android app, you're essentially telling Hilt to do some important work behind the scenes. This annotation triggers Hilt's code generation, which is a critical step in setting up dependency injection for your app. What happens next is that Hilt generates an application-level component. Think of this as the root of your dependency container, where all your app-wide dependencies will be managed. This setup is essential because it allows you to inject dependencies across your entire application seamlessly. Without this annotation, Hilt wouldn't be able to function properly. It's the foundation that enables Hilt to handle dependency injection at the application level. So, in the context of our overall theme, making dependency management easier and more efficient, this step is absolutely vital. It ensures that your app can leverage Hilt's full power right from the start. Now, let's take a closer look at the Hilt injectable classes. These are the core Android classes where Hilt can inject dependencies to help manage your app's architecture more effectively. Starting with application, which is annotated with @Hilt Android app, this is the entry point for Hilt in your app, enabling dependency injection across the entire application. Moving on to activities, these are subclasses of component activity, and they're also set up for injection. Each activity that needs dependencies will typically be annotated with @Android entry point. For fragments, since they are part of the AndroidX library, Hilt works with them as well, but they also need the @Android entry point annotation to enable injection. When it comes to the view layer, you need to use with fragment bindings to inject dependencies into your views, making UI components more testable and modular. Services are straightforward. They're the standard Android services, and with Hilt, you can inject dependencies into them as well, which is especially useful for background tasks. Broadcast receivers are also included in this list. They're the standard Android broadcast receivers, and Hilt allows dependency injection here too, simplifying the handling of system broadcasts. Finally, we have ViewModels, which are annotated with @Hilt ViewModel. This makes injecting dependencies into ViewModels clean and simple, aligning with modern MVVM architecture. Overall, these classes form the core touchpoints for dependency injection in Android with Hilt. Just remember, each of these classes, except for the application class, needs to be annotated with @Android entry point, which is what enables Hilt to inject dependencies seamlessly into your components. This approach helps us build more modular, testable, and maintainable Android applications. Now let's talk about Hilt dependency injection, starting with constructor injection. The key idea here is that you annotate the constructor of your class with @inject. For example, if you have an analytics service class, you would write it like this: class analytics service, then @inject constructor, and inside the parentheses, you specify the dependencies, such as private val API, analytics API. What happens is that Hilt takes care of creating and providing instances of these dependencies automatically, so you don't have to manually instantiate them. Moving on to field injection, this is another way to inject dependencies. In an @Android entry point class, like an activity, you declare a field that you want to inject by annotating it with @inject and using latinate var. For instance, in main activity, you would have @inject latinate var analytics service. When the activity is created, Hilt automatically injects the instance for you. Overall, both methods streamline dependency management, making our code cleaner and more modular. They connect directly to our main theme of simplifying complex dependency graphs in Android development with Hilt. Let's take a closer look at Hilt scoping. First, we have the @singleton annotation, which provides an application-wide scope. This means that objects annotated with @singleton will live for the entire lifetime of the application, and their lifecycle is managed by the singleton component. Essentially, these are shared instances that persist as long as the app is running. Next, there's @activity scoped. This scope ensures that a single instance of a dependency exists for the lifetime of a specific activity. It's managed by the activity component, so each activity gets its own instance, but that instance stays consistent throughout the activity's lifecycle. Then we have component-specific scopes like @ViewModel scoped and @fragment scoped. These annotations tie the lifecycle of injected objects directly to their respective components, such as a ViewModel or a fragment. This allows for precise control over how long dependencies live, aligning their lifetimes with the UI components they serve. The key takeaway here is that Hilt's scoping annotations enable us to manage instances efficiently. They make sure dependencies are reused appropriately within their defined lifecycles, which not only improves performance, but also helps prevent memory leaks by avoiding unnecessary object retention. Altogether, these scopes are a powerful tool in our dependency management arsenal, helping us build more robust and efficient apps. Thank you for reading. We hope this overview of key Android concepts has been helpful for your interview preparation. Remember, understanding these fundamental ideas, such as activities, fragments, intents, and the app lifecycle, is crucial for demonstrating your knowledge and confidence. Keep reviewing these concepts, and you'll be well equipped to showcase your skills. Best of luck with your interview, and thank you again for joining us on this learning journey.